Hello everybody! I just wanted to establish some basic facts and basic vocabulary about polynomials. Much of this you probably already know, but you might see some new things, and I'll try and be brief. These are both examples of polynomials. A polynomial is an expression that consists of multiple terms, each of which is a non-negative power of x. So x squared, x to the first, you could imagine this as x to the 0th power, and each of the terms can have a coefficient. Every polynomial has a degree, which is the term with the highest power. Sorry, it's not the term. The degree of the entire polynomial is given by the highest power term. So I would say that this entire polynomial is degree 101. A polynomial doesn't have to be written in a form where the highest degree term comes first. Like this is totally okay as a polynomial. Here the highest degree term is 100. It comes last. You notice that there are two different terms that are x to the 7th. So if you wanted to simplify this, you could combine those terms, but this is still a polynomial. It's also okay for your coefficients to be non-integers. So here we have pi and square root of 2, which are both irrational numbers, and that's also perfectly great. Just as a quick note, these are both not examples of polynomials. They are non-examples. X to the 7/2 plus x to the 1/2, because these exponents are not non-negative integers. They're equivalent to roots. Here we have more examples of exponents that are not non-negative integers. So x to the -2 is the same thing as 1 over x squared. And so again, these wouldn't fit our definition of a polynomial. Did I say definition? The general form for an nth degree polynomial is typically given this way. So you have a bunch of constants, a0, a1, a2, and so on. You have up to the nth term where the coefficient on that x to the n power is not 0, because if it were 0, then it wouldn't be an nth degree polynomial, it would be some smaller degree polynomial. So any expression that could be written in this form, that is algebraically equivalent to this form, would be a polynomial expression. An nth degree polynomial can be factored into n linear terms multiplied together that give the n roots for the polynomial. This fact is guaranteed by something called the fundamental theorem of algebra, which is really cool to prove, but actually is pretty difficult to prove. There's a couple of things to note about this, however. Well, first let me explain the notation here. So P is a constant that's a scaling factor on the outside. R1, R2, and so on up to Rn are all of the different roots or solutions to this polynomial. Something you should note is if R1 and R2 are actually the same root, you could simplify this by just having x minus r1 to the 2nd power and leaving this one off. So you can't have roots that are raised to larger powers if they're repeated. The second thing I wanted to say is more important, though. It is not guaranteed that all of these roots are real numbers. For example, let's compare x squared minus 1 to x squared plus 1. So both of these are second degree polynomials, so we know that the fundamental theorem of algebra guarantees that we can factor them into two factors that give the roots. So the roots of this are plus 1 and minus 1, and we know that it factors like this, x plus 1, x minus 1. What about this? Well, if you imagine the graph y equals x squared plus 1, it's an upward-facing parabola shifted up, so there are no x-intercepts, which tell us that there are no real roots. If you were going to try and solve this algebraically, though, if we were going to try and solve for this polynomial equals 0, you would get x squared equals -1, and then you could take the square root, and we'd get x equals plus or minus root -1. You may remember last year, there's a name for the square root of -1. The label that we attach to it is called I. So the roots here are actually plus or minus I. So this polynomial factors as x plus I and x minus I. So just be aware that that it may not factor into real values if the roots are complex. In our class, we'll call polynomials that can't be factored into real factors prime, by analogy with numbers, where a number is called prime if its only factors are itself and 1. So it can't be broken down into smaller factors. Finally, I wanted to end with sort of the big question, or a major question that you've been concerned with about polynomials, which is how to solve them. What you're doing when you're solving a polynomial is you're trying to figure out what are the roots, and you're trying to write those roots in terms of the coefficients. And it may not be familiar to you in this form, but consider if I have like 2x squared minus 3x plus 5 equals 0. What the quadratic formula is telling you is it's telling you how to figure out what the roots are, and the roots are all written in terms of this 2 and negative 3 and 5. So you're writing down the solutions to the equation based on the coefficients. So you know that when the polynomial is degree 2, that there's a nice formula that will tell you what the roots are in terms of the coefficients. What about higher degree polynomials? Like what if we have a 57th degree polynomial? Is there a nice process or a nice equation that will let us write the roots of this in terms of the coefficients? And so that's sort of a big question that we'll think about.